as saponification. This is an old way of making soap, is that people could take esters and treat this with something like sodium hydroxide, and it would be known as saponifying it. So what it looks like this does, though, is we're now going to generate the carboxylic acid. It's under basic conditions, so it's deprotonated. And because here we have a methyl ester, we have methanol as our byproduct. So based on what we've already discussed with other reactions, let's see if we can come up with a mechanism for this. We know this is Na plus OH minus, so that's a strong nucleophile. So let's go ahead. Oops, why don't and attack just this carbonyl group here. So I'll rewrite it down here a little bit larger. So Na plus OH minus, and let's have that attack, just like we've seen with our other reactions of aldehydes and ketones. We're going to form a tetrahedral intermediate. Notice now negative formal charges. Under acidic conditions, we have positive formal charges. Here, under the basic conditions, we have a negative formal charge. Now, we have a potential leaving group, both here with the OCH3 leaving or OH leaving. Now, if we have just the hydroxide leave, come and kick this, bring these electrons down and kick out the hydroxide, we're just going to go back to our starting materials. And so that is one possibility. And these reactions are not quite as reversible as the other ones. We'll just put the reversible arrows in. Instead, let's kick out this methoxide as a leaving group. So we're reforming our carbonyl carbon, OH, plus methoxide, OCH3 minus, as our leaving group. And now we're going to have a bit of acid-base chemistry at the end, because this is a relatively strong base, and we have this acidic proton with the carboxylic acid. We're going to have acid-base reaction. We're going to pull that proton off, and that will generate our final products. So this will generate our carboxylate, the conjugate base, and methanol. And we need to have this charge balanced, and so all along there's been a sodium around. So that is a mechanism that can describe this process of saponification. We start with our ester up here on the top, treat it with something like sodium hydroxide, and water is our solvent, and we end up with the carboxylate, that's the conjugate base of the carboxylic acid, the deprotonated form, and then methanol here because that's our ester. Now at the end, maybe you don't want this acid-base reaction to happen. You really want the carboxylic acid. It's just because this happens because of the basic conditions. And then you'd have to neutralize this if you really wanted to get the carboxylic acid. So Hannah asked a great question. When we're thinking about leaving groups and bases, and we had a bit of our discussion, I think it was yesterday and the day before, about pKa's and those types of things. This is a relatively strong base, which means it's not the greatest leaving group, say, compared to chloride. So chloride, with HCl having that pKa of -7, the chloride that's formed, the conjugate base, is stable. It's able to stabilize that negative charge. This one here, why don't we put it up here? This equilibrium of methanol going to H plus methoxide. The pKa of methanol is around 16. So that means this methanol is much less acidic than something like hydrochloric acid. It's close to water. But it's much more acidic than something like methane, so the CH4, where we saw that having aldehyde or ketone. This one here, if we're going to deprotonate this, it's the H plus, squeeze it in here, CH3 minus. This one has a pKa, we'll just say around 50. So this is by far methane, losing a carbon, let's say, for example, is a far weaker acid than the methanol here. In other words, this is a much, much stronger base than methoxide. So everything is relative. So the methoxide here is its leaving group, or if we have hydroxide as a leaving group, they're not nearly as good of a leaving group as the chloride, for example, and you're generating something that is a relatively strong base, if we wanted to use the word strong here. However, it's much less strong or weaker than something like CH3. So we're going to see groups that have these pKa's around like 16 to 20 or so that actually act as leaving groups. And so they can act as a leaving group. They're just not as good of a leaving group as some of those that we've seen already. So long-winded answer, excellent, to that question, but it's a great point to be thinking about. Something else, when we think about these equilibrium constants, this is somewhat irrelevant here, but remember, this is on a log scale too, the pKa values. So if you're looking at a difference of 1 pKa unit, that's the difference in the equilibrium constant on an order of magnitude. So I don't know about you, it just blows my mind when you think about these huge differences. If you're looking at, 9 pKa units, it's a billion times difference. And then if you're looking at these sorts of numbers, it's just amazing how different the equilibrium constants are. I see another question, Oriane. So why wouldn't the oxygen from water, let's put water in here, grab from the ester, see, why wouldn't the oxygen from the ester grab a proton from water? Oh, so great question as well. Here, I think if we're referring to the starting material here, so let's move the water up here as well. And it doesn't really look like water. Can't erase with the pointer. Let's try this again. A lot of this comes down to different sorts of acid-base chemistry that can happen, and the favorability of those proton transfers. When we've been protonating the carbonyl group here, we've been using H3O+, because that has a pK, H3O+, if I protonated this, about minus 1.7, which actually makes it favorable to protonate this group here. Protonating this oxygen here is going to be relatively unfavorable, and only in the presence of a stronger acid would you be able to protonate here. So I see what you're saying is, why not just turn this relatively bad leaving group or worse leaving group into a good leaving group? And you're exactly right that one might like to do that. However, we don't have acid around in this reaction. So we're doing this reaction in the presence of sodium hydroxide, a base, and water. So the hydroxide occasionally will pull a proton off of water, generating just hydroxide, it's just switching back and forth. However, without having a strong enough acid to actually protonate this methoxide, we cannot do that here under these basic conditions. But we don't have to, because the methoxide here, even though it's not the greatest leaving group, it still is a leaving group. And so this intermediate is a pretty high energy intermediate with a negative charge on the oxygen. So we're going to gain, it's going to be energetically favorable, I should say, to reform the carbonyl group, which helps pay part of the price to kick out the methoxide. Okay, excellent. So that's the base mechanism. And now let's look at a couple of other mechanisms that essentially follow the same trend, but rather than having something like hydroxide, we'll have a different nucleophile. And you'll see the same trends that we also saw with the acyl chloride, just that we have not as good of a leaving group overall. So let's take this ester, and let's react this with lithium aluminum hydride in ether. And maybe to make it more clear, I'll say excess here. So it's excess or 2 equivalents. And actually, not excess ether. How about excess? This one is in excess. Notice we go from an ester all the way down to a primary alcohol. So that actually looks very similar to what we saw before with the acyl chloride. If instead we wanted to actually stop, let's say at an aldehyde here, we can use our reagent as dibol, or dibol H, again, which is, we're not going through the mechanism, we're leaving that it's a bit of a mystery, but that would be a way of reducing an ester to an aldehyde. Let's just consider the lithium aluminum hydride and see if we can make sense of this with what we've already seen. So let's have an ester. Why don't we make it a methyl ester, just a little easier to see. And we saw that lithium aluminum hydride is supplying essentially H-. We're not going to draw the whole reagent here. Just going to attack forming a tetrahedral intermediate, so OCH3. There's the hydride that we've now added. And just like before with the acyl chloride, now we do have this leaving group. Not the greatest leaving group again, but it is a leaving group. It's methoxide or whatever that ester might have been. So we'll kick this out. We're reforming our carbonyl group. And now notice we have an aldehyde. And so this is where if we have the sterically hindered reagent like the diball, that's why we can stop at the aldehyde. But we know lithium aluminum hydride, LiAlH4, will reduce the aldehyde. So the reaction happens this again. Hydride is going to attack the aldehydes, carbonyl carbon. Second tetrahedral intermediate now, 2 hydrogens. Now we don't have a leaving group, not even a leaving group like methoxide. So we just have 2 hydrogens, and this happens to be a methyl group here. So we just wait until we add water to the reaction, and we'll protonate this to generate our primary alcohol. We'd have some hydroxide and the rest of the lithium aluminum hydride reagent. So just like the acyl chloride here, when we carry out the hydride reduction reaction, it's happening in 2 sequential reduction reactions. First, the ester is reduced down to this aldehyde, and then because the lithium aluminum hydride can react with the aldehyde, then we go down to the primary alcohol. So you could actually use water or acid in this particular case. I think maybe in the past we've used acid. Sometimes it's acid, or sometimes it's water. In response to Crystal's question. So it's a good point. And, a lot of times it probably would be even better to use just slightly acidified water, so that, because otherwise you're going to end up with a mixture of these 2 species here, because actually the pKa, this is ethanol here that we're forming in the end. So this is ethoxide, this is ethanol, so that is the pKa just slightly higher than water. The methyl groups here, the carbon is slightly electron donated. Okay, how about organometallic reagent like a Grignard reagent? So this also looks similar to something that we've seen perhaps. We could start out with this ester, and it looks like you were reacting this with this Grignard reagent, and then this time we'll use acid at the end. And this one, maybe let's say we also have an excess, just to be clear, of that Grignard reagent. And it looks like we're adding 2 of those benzene rings. So I'm assuming it's probably going to go by, most likely, similar mechanism. There we go. So now let's have our Grignard reagent attack. We're going to form our tetrahedral intermediate. So make it larger here. Formed our new carbon-carbon bond. Looks like that's where we've added one of our benzene rings. And now again, we have this potential leaving group here. It happens to be methoxide in each case here. It doesn't have to be, the R group could be different. So we'll kick that out. Reform our carbonyl group. Put this down here. We've lost methoxide. And now notice we have a ketone. So we could have another one of our Grignard reagent equivalents. Put it up here for space. Have this attack. Second tetrahedral intermediate. And now we have our carbons connected to this carbon that has the oxyanion on it. So we do not have any good leaving groups. Now let's add acid this time. Just to push this towards protonation. And this gives us that same product that's just written above it. Oh, I'm not sure what happened there. Okay. Okay, so that's the product in the end. So what we'll notice in a lot of these reactions here is we're starting out with an ester, and somewhere here in the middle, here's our, so it's not an aldehyde, it's a ketone, and then we end up, in this case, with an alcohol in the end. So it's very useful to carry out these different sorts of transformations. There's a lot of interesting chemistry that we can conduct here, but the ester, mechanistically, notice here, two reactions with the organometallic reagents. First, to form the ketone, forming a new carbon-carbon bond, and then same Grignard addition that we've seen already to ketones to form this product here. Now we no longer have any good leaving groups or any sorts of leaving groups, so we'll protonate to generate the final product. And notice that parallels what we saw with the hydride. So that here we have a Grignard reagent in the kind of in the middle left here, as opposed to a hydride. But the mechanism, as we're drawing it, is essentially the same. And why don't I make this complete here? Let's put in our NGBr counter ion here and here. This hydride one, this would actually be coordinated to the aluminum, but we didn't put that in. Okay.